Welcome to the Sleepy Voyager. If you love soothing space mysteries and you want more sleepy documentaries like this, tap subscribe and turn on the little bell. It really helps the channel, and it means you'll never miss our next gentle cosmic wonder. 3I Atlas is an object from outside our solar system. 3I means it is the third confirmed interstellar object we have seen, after 1I/Oumuamua and 2I/Borisov. Atlas is the survey that found it. The Asteroid Terrestrial Impact Last Alert System, a set of robotic telescopes that scan the sky for moving objects. When astronomers looked at the path of this object, they saw that it was not following a closed loop around the Sun. Instead, it was on a hyperbolic path. That tells us it is just passing through our solar system and then leaving again. In simple words, it came from another star system, it will swing by the Sun, and then it will go back out into space. Interstellar objects are rare to catch because space is huge and these visitors are usually small and dark. Surveys like Atlas take many pictures of the same parts of the sky and use software to spot tiny dots that change position from one picture to the next. If a dot moves in a straight, steady way that does not match the orbits of local asteroids and comets, astronomers pay attention. They measure the position very precisely, night after night, and fit a path to the data. If that path says hyperbola, and the speed is higher than the Sun's gravity can hold, the object is interstellar. That is what happened here. You might wonder what 3I Atlas is made of. From what we know about similar objects, it is likely a mix of rock, dust, and ices such as water, carbon monoxide, and carbon dioxide. In sunlight, those ices can warm up and release gas and dust, making a fuzzy glow called a coma and sometimes a tail. However, not every object will show a bright tail, especially if it is small, dark, or far from the Sun. So do not expect a huge dramatic sight in the sky. Most people will not see 3I Atlas without a telescope or a sensitive camera. Safety is easy to explain. 3I Atlas is not on a path that comes close to Earth. It is a distant passerby. Astronomers track these paths carefully and share the numbers with the worldwide community, so if anything changed, we would know. But with an interstellar hyperbolic orbit, the basic idea is simple. In once, out once. No repeating visits. The name and the numbers tell us a lot. 3I marks its place in the short list of interstellar visitors we have found so far. Atlas tells you which survey first reported it. The measured speed and shape of the orbit confirm that the Sun cannot capture it. The angle of the path across our sky explains which constellations it appears to pass through. None of this means the object is aiming at those stars. It is just our line of sight from Earth. The background stars are like a fixed grid we use to describe positions, the same way we use latitude and longitude on Earth. Seeing something this rare helps science in practical ways. When sunlight hits 3I Atlas, its surface and any gases it releases reflect light in specific patterns. By spreading that light into a rainbow, called a spectrum, scientists can look for chemical fingerprints. That teaches us about the building blocks found around other stars. We can compare those fingerprints to the ones we see in comets born in our own solar system. If they match, that suggests planet-forming materials are similar in many places. If they differ, that tells us other systems can be built in different ways. Observing an interstellar object is also a good test of our tools. Telescopes, tracking software, image processing, and orbit-fitting methods all get a workout. Because the object moves against the star background a little differently than a normal comet or asteroid, teams can check that their systems still lock on, still measure brightness correctly, and still deliver solid orbits. That improves our ability to find and study future visitors. If you are curious as how to find it at home, the simple answer is that most people cannot with the naked eye. Amateur astronomers use star charts or mobile apps to get the coordinates for a given time and place. They point a telescope or a camera mount to those coordinates and take longer exposures to collect enough light. The object appears as the faint smudge or the tiny streak, depending on the tracking method. If you check again the next night at a similar sidereal time, you will see it has shifted a little on the image. That shift is the motion that proves it is real and not just a camera artifact. It is normal to ask where 3i Atlas came from originally. We do not know the exact star system. A common idea is that when planets form around young stars, many small icy bodies get kicked around by gravity. Some are thrown inward and melt. Some are thrown outward so fast that they escape into interstellar space. After that, they drift for very long times until they cross paths with other stars, like our Sun. Every once in a while one lines up so we can see it. It is also normal to ask whether we will send a spacecraft to it. In general, that is very difficult. Interstellar objects move fast and are only discovered when they are already quite close in astronomical terms. Building, launching, and guiding a mission fast enough to catch up is a major challenge. Scientists are studying ways to do this in the future, but for now, most of our information comes from telescopes on Earth and in space. In short, 3i Atlas is a small faint visitor from another star system, detected by careful sky surveys, confirmed by its hyperbolic path, and observed to learn about the materials that form worlds. It is not a threat, it will not loop back, and it teaches us that our solar system is part of a larger neighbourhood filled with many kinds of objects. Watching it is like opening a window for a moment and letting in fresh air from far away, only this time the air is data, and the breeze is the path of an object that reminds us we live in a connected universe. The simplest way to understand 3i Atlas's trip is to picture a wide open curve that comes in from far away, sweeps past the Sun once, and then continues back out without looping. That open curve is called a hyperbola, and it's what we get when the object's total energy is positive and its orbital eccentricity is greater than 1, which means the Sun's gravity can bend its path but cannot capture it into a permanent orbit. On such a path there are two straight line directions that matter: the inbound direction it was following before we ever saw it, and the outbound direction it will follow after it leaves. Astronomers call these the asymptotes, and the small angle between them is the deflection caused by the Sun's pull. If you keep hearing the term v infinity, written v infinity, that is the object's coasting speed far from the Sun, its cruise speed out in interstellar space, and a non-zero v infinity is another clear sign that the object is unbound. Because the orbit is unbound, there is no future next time around, and because the Earth is only in one place along its own nearly circular path at any given date, the geometry never lines up for a close pass. In plain language, it is a passerby moving briskly on a safe one-time fly-through. As it approaches the Sun, the object accelerates a little due to gravity, reaches its closest point to the Sun, perihelion, then slows again as it climbs back out. That smooth speed up and slow down happens to every comet and asteroid, but for an interstellar one the whole arc is steeper and the exit is final. From our point of view on Earth, what you'll notice is that the object's apparent motion against the star background changes over time. Far away it seems to crawl. Near perihelion, it can drift faster across a camera field from night to night, and then it quiets down again as distance grows. That change in apparent speed is normal and simply reflects the changing triangle made by the Sun, the Earth and the object. Another factor is solar elongation, which is the angle between the Sun and the object on our sky. When the elongation is large, the object is up in a dark sky and easiest to attempt. When it is small, it's lost in twilight or even the Sun's glare, so observers end up with short, repeating windows at similar times of night or morning. Brightness will also follow a gentle pattern, generally increasing as it comes inward, peaking around the time the geometry and distance are most favourable, and there fading as it recedes. Whether it ever becomes easier to see is set by size, reflectivity, albedo, and whether sunlight warms any surface ices enough to release gas and dust that create a subtle coma. Many interstellar visitors stay faint, so most views are through telescopes or long exposure images rather than with the naked eye. The path itself is computed from repeated measurements of position on the sky. Each measurement adds a dot, and fitting many dots gives the orbit. Early on the uncertainties are larger, but as more nights of data arrive, the solution locks in and the tube of possible futures shrinks to a tight line, which is how teams can say with confidence that there's no Earth encounter and no bound return. Planetary gravity does tug a little as it passes. Jupiter, for instance, can add a tiny nudge, but for a fast interstellar object, these tugs usually amount to small course corrections, not a capture. There is no resonance with planets because resonance belongs to repeating orbits, and this one does not repeat. Non-gravitational forces, like a gentle rocket effect from any one-sided outgassing, can be present but are typically small. If they exist, they're included in refined orbit models using simple parameters so the predictions remain accurate. If you watch the numbers astronomers publish, you will see coordinates, right ascension and declination, predicted magnitudes, the rate of motion in arcseconds per minute, and occasionally the phase angle, which tells you the Sun-object-Earth angle and helps explain how bright the object will look. Higher phase angles can highlight dust if there is any. Lower phase angles can make the object appear more neutral and compact. Nothing about this journey implies danger. The combination of an unbound trajectory, a safe missed distance, and a steadily improving orbit solution all point to a quiet visit with plenty of room between the object and our world. In short, the calm truth is that we are witnessing a clean, once-through passage shaped by gravity's predictable mathematics. In from interstellar space with a non-zero V infinity, a single graceful swing by the sun at perihelion, and then back to the deep where it will continue on a new straight path forever, while we collect light, logs, and lessons as it goes by. When people say the object keeps returning to the same coordinates, they're usually bumping into how the sky is mapped and how our daily observing habits work, not anything magical about the object itself. Astronomers describe positions using right ascension RA and declination DC, which are like longitude and latitude projected onto the sky. And those coordinates are fixed to the distant stars, not to the sun, the moon, or moving objects like comets. So when your mount slews to a stored RA/DEC, it is pointing at the same place on the star background every time, regardless of whether the comet has already drifted on. Now add Earth's rotation. The stars return to the same orientation after one sidereal day, which is about 23 hours and 56 minutes, roughly 4 minutes shorter than our 24-hour civil day, and that 4-minute offset is the quiet trick behind the déjà vu. If you go outside at the same clock time night after night, you're actually observing about 4 minutes later in sidereal time each day, so the same RA crosses your local meridian a little earlier, and if your routine centres around a fixed after-dinner slot or a fixed dawn slot, you end up looking at nearly the same RA/DEC slice, even though the date changed. This alone can make it seem like the comet returns because your telescope keeps revisiting the same Starfield, while the comet's motion from one night to the next is small enough to stay inside the same eyepiece or camera frame. If your software rounds coordinates to the nearest arc minute, or if you manually centre the fuzz by eye, your logbook can show repeated RA/DEC entries within the rounding error. There are a few more nudges that reinforce the effect. Most of us observe when the object's solar elongation makes it accessible, for example, just after evening twilight or just before morning twilight, and those windows shift slowly, so our sessions naturally cluster around similar local sidereal times, which means similar coordinates. A telescope mount in equatorial mode tracks the sky's rotation by moving steadily in RA, making the fixed grid nature of RA/DEC feel normal, while the comet's proper motion rides on top as a gentle drift that may be hard to appreciate unless you compare stacked images or precisely plate solve. If you use an Alt-Az mount, altitude azimuth, you still usually plan the pointing in RA/DEC from your app or Ephemeris, so the planning coordinates repeat even if the on-mount readout is ALT/AZ, and because many phone apps default to showing object positions for the next convenient hour mark, each 2100, you can get identical predicted coordinates over multiple nights if the object's motion between those rounded times is smaller than the display precision. Topocentric versus geocentric coordinates add another subtle layer. Most observers use topocentric positions from your spot on Earth, which include a tiny nightly parallax due to your location and Earth's rotation, but for distant slow movers this change is small, so the numbers look the same unless you zoom in. Precession and nutation, the slow wobble of Earth's axis, do shift RA/DEC over months to years, but night to night they're negligible, so they don't rescue you from the sameness. Atmospheric refraction can slightly change the apparent altitude near the horizon, but doesn't change the RA/DEC printed from a catalogue. So again, your software keeps feeding you the same grid reference while the object ambles along inside the frame. Practical examples make this concrete. Suppose your camera field of view is 1 degree across and the comet moves 10 arc minutes per day. After 3 days, it has only shifted half a degree. The same bright triangle of stars still dominates your composition, and your centering routine still drops the target near the same pixel area, which leads you to write down essentially the same coordinates, especially if you record to 1 decimal minute, 6 arc seconds, or worse. If you want to see the motion more clearly and avoid the same coordinates trap, you can try simple tweaks. Observe at the same sidereal time rather than the same clock time, shift your start about 4 minutes earlier each night, or deliberately change your clock time by 20 to 30 minutes from one session to the next to catch a different hour angle, or plate solve each image and annotate the comet's centroid in RA/DEC to second level precision so small changes stand out, or enable track at comet rate in your mount or guiding software so the comet stays fixed and the stars streak, which makes its motion undeniable. You can also compare geocentric ephemerides to topocentric ones in your planetarium app to appreciate parallax and plot rate of motion, arc seconds per minute, versus date to know when the drift will be most obvious. The bottom line is that the sky coordinate system is a fixed map painted on the celestial sphere. Our daily observing routines tend to revisit the same map tiles because of the sidereal day offset and repeating twilight windows, and rounding plate scale and slow motion keep the numbers looking familiar. So it's perfectly normal for a log to show the same coordinates while the comet is in fact advancing smoothly along its predicted path. When we point at an object like 3i Atlas, we're juggling several frames at once. The object moves in space, Earth spins and orbits, our telescope mount has its own coordinate system, and our camera records positions in pixels, so it helps to untangle these layers and see how they fit together. Start with the sky map itself, right ascension and declination, which are like longitude and latitude painted on a giant sphere centered on Earth, which we treat as fixed to the distant stars, and that's the reference your planetarium app shows when it says, go to RA 12 hours 34 minutes, dec plus 15 degrees, 20 degrees, but those RA/DEC can be described in slightly different ways depending on the frame and the corrections you apply. Geocentric means as seen from Earth's scatter, topocentric means from your observing spot, which adds a small shift called parallax because you're not at the centre. For a very distant object, the geocentric and topocentric coordinates are almost the same, but for nearby things like the Moon, the difference is obvious. And interstellar objects sit in between, not as extreme as the Moon, yet close enough that careful observers still use topocentric ephemerides generated for their exact location. Then there's heliocentric, sun-centered, and even barycentric, center of mass of the solar system, frames used by professionals for orbit calculations because gravity plays nicest in a sun-centered or barycentric inertial frame where Earth isn't constantly shifting the origin, and when you see an osculating orbit listed at the J2000 epoch, that means the orbital elements are expressed relative to a standard reference plane and equinox defined for the year 2000. This gives everyone the same baseline. On top of the frame choice come corrections for the world we actually live in. Earth's axis slowly wobbles, precession, and nods, nutation, so the RA/DEC grid slides a little over years and decades, and your software either outputs positions in a fixed standard like J2000, or in of-date coordinates that include that small drift. Light doesn't arrive instantly, so there's also light time correction. Your now positions really describe where the object was a few minutes ago, because that's how long the photons took to reach you. And if you want positions as they actually appear in the eyepiece at this moment, you can include annual aberration, an apparent shift from Earth's orbital speed, diurnal aberration, a tiny extra from Earth's rotation, and atmospheric refraction, bending of light near the horizon that lifts objects a bit higher than their geometric position. Refraction changes the apparent altitude, not the underlying RA/DEC, but when you look through an eyepiece, the object is where the air has placed it. Now switch to the telescope. An equatorial mount tracks the sky by turning a single axis at the sidereal rate, essentially living in the RA/DEC frame, while an alt-az mount lives in the local horizon frame, altitude and azimuth, and must drive both axes continuously and accept field rotation during long exposures unless you use a field derotator or an equatorial wedge. The mount's go-to system translates the target's RA/DEC into the mount's own axis using your time, location, and a pointing model learned during alignment. And small things like a cone error between the optical axis and the mount, flexure under weight, or temperature changes create offsets that guiding then cleans up by watching a guide star on a small camera and nudging the mount so that the star stays still. In the meantime, the object itself has proper motion across the star background driven by its real 3D path and our changing vantage point. So you can choose to track at sidereal rate, stars stay sharp, fast object streak, or at the object's custom rate, the object stays sharp, stars trail. And many software tools can send that custom rate to the mount if the rate is modest. When the camera collects photons, everything turns into a third frame. Pixel coordinates, measured in rows and columns. To connect pixels back to sky, you plate solve. Software finds patterns of stars in your image, matches them to a catalogue, and writes a world coordinate system, WCS, into the image header so each pixel maps to an RA/DEC. With WCS, you can measure the object's centroid to fractions of a pixel, convert that to RA/DEC, and watch the drift night by night in a clean, frame-aware way. Timekeeping is its own layer. Orbit solutions and Ephemeris often reference TT, terrestrial time, or TDB, a relativistic barocentric time, while your laptop runs UTC, coordinated universal time, which adds leaps and seconds, so your software quietly converts between these scales when generating predictions, because a 1-minute timing mistake can shift a fast mover by many arc seconds. Because Earth rotates relative to the Starfield in the 23 hours, 56 meters a sidereal day, observing at the same civil clock time puts you at a slightly different orientation in the RA/DEC frame each night, which is why same coordinates at the same clock time can still happen if the object's nightly motion is small and your field of view is large. Another important subtlety is apparent versus mean place. Apparent places include the short-term wiggles, aberration, nutation, and refraction, and are best for pointing a telescope right now, while mean places live in a cleaner, long-term grid like J2000 that's best for archiving, catalogues, and comparing measurements over years. Professional orbit fitting will typically transform all observations into a consistent inertial frame, often barycentric, with light time and relativity handled, fit the trajectory under gravity, and small non-gravitational accelerations if outgassing is detected, and then transform the resulting state vectors back into topocentric apparent RA/DEC for each site and time so observers can point accurately. For a practical mental model, think of nested shells, the inertial solar system frame where the object's path is a clean curve, the Earth-centered frame that adds our yearly loop, the local topocentric frame that adds daily spin and parallax, the mount frame that turns those into motor steps, and the sensor frame that records the final result as pixels. If anyone's shell is misunderstood, wrong time, wrong location, geocentric numbers used for a topocentric session, refraction ignored near the horizon, You can end up thinking the object returns or stands still, when in fact you've just revisited the same fixed star tile with different small offsets. Once you grasp these frames, you can make better choices. Use topocentric apparent coordinates for tonight's pointing. Record J 2000RA/DEC plus exact UTC timestamps for your archive. Plate solve every exposure to remove guesswork. Enable comet rate tracking when the rate exceeds a few arcseconds per minute. Avoid low altitudes where refraction distorts positions. And if you want to feel the moving frames directly, capture 2 short sequences an hour apart and blink them. Stars will shift a little from field rotation on an ALTAS rig, while the comet slides in a different direction, neatly revealing Earth's spin, your mount's frame and the comet's own frame all at once. The feeling that 3i Atlas barely moves, a gentle, almost stubborn stillness, often starts with how slowly faint objects shift compared with the size of a typical camera frame and the limits of our eyes and gear. Imagine a telescope camera setup with a 1.5 degree field of view, that's 90 arc minutes across, and a target creeping at 8 to 12 arc minutes per day. From one night to the next, the object advances only a tenth of your frame's width, so the same bright asterisms dominate each image, and your brain anchors on them, concluding, same place, even though a careful overlay would reveal a real offset. Shrink the nightly change further by observing at nearly the same sidereal time, and the background stars line up almost perfectly, erasing visual cues of motion unless you measure precisely. Now add pixel scale, say your camera samples at 1.5 inches per pixel, and typical seeing blurs stars to 3 to 4 pixels, FWHM, then a 20 to 30 arcsecond shift from one evening to the next becomes only 13 to 20 pixels of motion, easy to miss by eye when you're centering a soft, low contrast patch, and even easier to hide if you crop or recenter frames during processing. Rounding amplifies the illusion. Logbooks kept to the nearest arc minute, 60 arc seconds, will show identical RA/DEC on nights when the target actually moved 30 to 50 inches, because your recording precision is coarser than the motion, and many planetarium apps default to displaying coordinates to 0.1 arc minute or 1 arc minute to keep screens uncluttered, which quietly bins different positions into the same readout. Guiding and tracking add another soft blanket over motion. If you track at the sidereal rate, the stars look perfect and the comet smears slightly during long exposures, but short sub-frames, 30 to 60 seconds, will make both look sharp, hiding the smear and taming the sense of drift. While if you guide on the comet's rate, the stars trail and you might crop them out later, again removing the most obvious arrow that shows the object moved. Mechanical behaviours conspire too: periodic error in the right ascension worm, small declination backlash, and differential flexure between the imaging scope and the guide scope can shift star positions by tens of arcseconds over a session, which your plate solving or registration software later cancels out to align images perfectly on the stars, inadvertently aligning away the comet's tiny inter-night displacement as well. Even the atmosphere helps the illusion along, seeing blurs the comet's coma into a soft disk that expands and contracts frame to frame, making the centroid depend on noise, sky background, and how aggressively you stretch the image. So 2 measurements taken with different stretches can land on the same rounded coordinate even when the underlying centroid differs by several arcseconds. Exposure time matters. A 3-minute exposure at 0.3 R. Seconds per second apparent motion yields a 54-inch trail, which is obvious, but a 30-second exposure at 0.1 inch per second yields only 3 inches of motion, essentially hidden inside the seeing disk, and stacking many short subs with star-aligned registration averages, the comet into a roundish blur that seems nailed to the same place. Human vision brings its own biases. Our pattern detector latches onto familiar triangles and lines in the Starfield, a phenomenon called pareidolia, and once we decide this is the place with the skinny triangle and the squashed kite, we experience confirmation bias, interpreting tiny differences as the same and ignoring misfits as noise. Software defaults reinforce this. Some apps quantize predicted positions to the nearest minute of time and tenth of a degree on casual screens, some round rate of motion to 1 decimal arc seconds per minute, and some reuse cached ephemerides unless you hit refresh, leading to identical coordinate readouts on back-to-back nights for a slow mover. Timing and time zones sneak in as well. If you plan by local clock time while daylight saving shifts the wall clock, or you let a laptop drift a minute from true UTC, you may repeatedly sample the same hour angle without realizing it. Landing the object near the same detector region and writing down the same rounded RA/DEC, camera rotation can mask progress. If you rotate the imaging train between nights to fit a framing idea, and then use star-based registration, the software rotates and translates frames to perfect star congruence, which makes subtle target motion appear as a near pure translation that the brain doesn't flag as movement the way a trail would. Catalogue choices add another layer. Different star catalogues can shift WCS solutions by a fraction of an arc second to a few arc seconds in crowded fields, and if you switch catalogues between nights, the small systematic differences can push measured comet positions toward the same rounded bin, ironically making two different nights look the same numerically. There's also the centroiding method, measuring the brightest pixel, a flux-weighted centroid, or a PSF fit can give slightly different answers for a fuzzy, asymmetric coma, sunward jets, background gradients, or a faint star blending into the coma all bias the centroid a little, and if one night's bias is positive and the next night's is negative, their rounded outputs might coincide to the nearest arc minute. Practical numbers make this concrete. At 1.2 arc seconds per pixel, a nightly shift of 24 inches is 20 pixels, noticeable if you blink 2 frames, but easy to miss when you compare separate screenshots with different crops and stretches. If your notes record RA to the nearest second of time, approximately 15 inches on the sky, and DEC to the nearest 10 inches, then any motion smaller than these bins often collapses to no change, especially if plate solve solutions vary by a few arc seconds. To cut through the illusion, small workflow tweaks help. Refresh ephemerides each session and display RA/DEC to at least 1 inch precision. Plate solve every frame and annotate the comet's centroid with the same method each night. Blink aligned images rather than comparing stills. When possible, run 2 tracking modes, one star track stack and one comet track stack, so you can see both the stationary star view and the stationary comet view. Vary your observing time by 20 to 40 minutes between nights to change the hour angle, and break the same sidereal slice habit. Log the apparent rate of motion, arc seconds per minute, and total expected nightly displacement, arc seconds per minute, 24 hours, alongside your coordinates so your eye knows what to look for. If your field is very wide, punch in with a longer focal length or crop to a smaller box so the same absolute shift fills more of the frame. And if the comet is extremely faint, use consistent image stretches or better. Measure photometry and astrometry on the linear data before any non-linear processing, keeping the centroid honest even when your eyes are convinced the sky has paused. Taken together, slow intrinsic motion, big fields of view, rounding, guiding, stacking practices, atmospheric blur, mechanical idiosyncrasies, and our own pattern-seeking brains weave the gentle illusion that the object sits still or returns to the same coordinates, when precise, consistent measurements reveal a steady, predictable drift, night after night. Where an object appears to travel depends as much on the background tapestry as on the object itself, and the star crowd behind 3i Atlas can make different nights feel uncannily similar. When the path crosses dense regions of the Milky Way, low galactic latitudes where our line of sight looks through the disk, the field overflows with faint pinpoints, mottled nebulae, and open clusters, and this richness creates powerful visual anchors, repeating triangles, crooked lines, and tiny kites of stars that look the same even when the object has moved a small but real distance. In sparse, high-latitude fields, A displacement of 20 or 30 arc minutes is obvious because there are few bright stars to confuse the eye, but near the Milky Way bulge or along busy constellation spines like Cygnus, Sagittarius or Cassiopeia, the same size shift can pass unnoticed because the pattern density overwhelms our ability to track change. Small telescopes and camera lenses with wide fields of view amplify this effect. If your frame spans 2 to 5 degrees, one sequence of recognizable asterisms can dominate your composition for a week, giving the strong impression of same coordinates even as the object marches across the frame. The ecliptic adds another layer. Many comets and asteroids roam roughly near the Sun's path, where starfields also host the zodiacal constellations and frequent open clusters. So the sky behind the target is not only crowded but familiar, and the human brain, which loves to categorize, happily labels the area as the one with that little arrow-shaped trio next to the faint puff, reinforcing memory over measurement. Confusion noise matters. Too faint background galaxies, unresolved star blends, and subtle nebulosity brighten the sky in patchy ways that pull your eye to the same patches night after night. So even when you recenter carefully, you may pick the same bright micropattern as your guide and land the object near the same detector region. Star clusters are repeat offenders in this illusion. Pass near the outskirts of M11, the wild duck cluster, or the double cluster, and you'll keep seeing the same splash of grainy stars framing the target, because the cluster's recognizable texture hardly changes across small sloughs, while the comet's nightly drift is swallowed by the field's sameness. In narrowband or light-polluted skies, the crowding problem can intensify because stars dim unevenly. Light pollution suppresses fainter stars more than bright ones, and filters reshape the mix of visible stars, leaving a subset of medium-bright reference points that repeat across a swath of sky and make frames rhyme with one another. Optics and focus choices feed into this. A slightly soft focus, common for long sleepy sessions, rounds and enlarges. Stellar profiles so more faint stars peak above the noise, thickening the background and making it harder to spot a low-contrast smudge's change in position. While a crisp, undersampled image with small star images makes motion stand out because the comet's coma looks different than a pinprick. At the plate-solving level, catalogue selection influences perceived sameness. Using a deep catalogue like Gaia DR3 exposes a blizzard of stars and produces extremely stable solutions that align frames to subarc, second precision. So the stars lock in and the comet's gentle drift requires careful centroiding to notice, whereas a shallower catalogue can wobble solutions by a few arc-seconds in crowded zones, and, ironically, return nearly identical rounded coordinates across different nights, because those tiny plate-solve shifts counteract the comet's small motion. Photometric gradients in crowded fields can also tug measured centroids. A faint star under the comet's coma one night and gone the next, because of seeing or stretch will bias the measured center toward or away from that spot, yielding coordinates that look unchanged to the nearest arc minute even when the true position moved. Practical observing plays a role. Star hopping often uses distinctive mini-asterisms, little hooks, diamonds, or crooked wands to land in the right area, and once you commit those shapes to memory, your hop reproduces nearly the same pointing, so the background déjà vu is baked into your method, while go-to mounts that sync on a nearby bright star in a dense field can inherit subtle pointing biases that place the object on the same chip quadrant repeatedly. The cure is not to avoid crowded skies, but to lean into quantitative habits. Plate solve every exposure and annotate the comet's centroid to arcsecond precision. Blink 2 nights of images with the stars not perfectly registered, so the background shifts and the comet's path pops out, then blink again, star registered, and look for the comet's drift relative to fixed points. Change scale if you can, crop tighter or switch to a longer focal length, so that a 10 to 20 arc-minute nightly shift spans a meaningful fraction of the frame. Vary the observing time by half an hour from one night to the next to alter the hour angle and star pattern orientation, which helps your brain notice change. When the field is extremely busy, try comet rate tracking for a short sequence so the comet becomes the fixed object and the rich star crowd smears into short dashes, instantly proving motion. Log the galactic latitude alongside each session to anticipate crowding. Vertical bar B vertical bar less than 10 degrees usually means dense star fields and familiar patterns that repeat, while the absolute value of B greater than 30 degrees tends to be cleaner and more revealing. If nebulosity is present, use a broadband luminance or clear filter and keep stretches consistent between nights to avoid mistaking contrast changes for position changes. Be aware of variable stars and background galaxies near the path. Small changes in their appearance can anchor your centering to the same place, and if you are composing pretty pictures, consider keeping one or two bright reference stars out of the exact center on purpose so you are less tempted to reframe by using the same anchor each night. Because the more the constellation backdrop recurs in the same arrangement, the more certain it will feel that the object hasn't moved, even though precise measurements will show a steady, predictable walk across the crowded, starry quilt. Solar elongation is simply the angle between the Sun and the target, and will do it as seen from Earth, and it quietly controls when and how well you can observe something like 3-eye atlas. A large elongation means the object sits far from the Sun on the sky and can be placed in truly dark hours, while a small elongation squeezes it into dusk or dawn, forcing short sessions and repeatable viewing windows that make many nights feel the same. You can imagine elongation as the separation you'd measure with a giant protractor centered at your eye. Point one arm at the Sun, the other at the comet, and read the angle. 180 degrees is directly opposite the Sun, midnight, best darkness. 90 degrees sits roughly overhead around sunset or sunrise. 0 degrees is solar conjunction, lost in glare. Because Earth orbits the Sun while the comet is on its own path, that angle changes day by day, and the change sets your observing schedule more than almost anything else. When elongation is shrinking toward conjunction, the object gets trapped closer to twilight, low altitude, bright sky, heavy atmospheric extinction, and you find yourself going out at almost the same civil time each evening trying to catch it in the last clear minutes before it sinks. After conjunction, the geometry flips and the object reappears in the morning sky at roughly the same small elongation it had before, gifting a near mirror image observing window just before sunrise. Twilight structure matters. Civil twilight, Sun 0 to 6 degrees below the horizon, leaves the sky bright and blue. Nautical twilight, Sun 6 to 12 degrees down, is darker but still washed. Astronomical twilight, Sun 12 to 18 degrees down, is where the Milky Way and faint fuzzies come back. A comet at 20 to 30 degrees elongation will often be accessible only during civil or nautical twilight, with a sky background 10 to 100 times brighter than full darkness, which can bury a diffuse coma unless you use longer exposures, larger apertures, or more aggressive stacking. Altitude couples to elongation through the object's ecliptic latitude and your latitude on Earth. Two targets with the same elongation can have very different altitudes at the end of twilight. Low altitude means you are looking through more air mass, secant of the zenith angle as a first approximation, and each extra air mass costs you magnitude through atmospheric extinction, typically approximately 0.15 to 0.4 magnitude per air mass for broadband, visual, or worse near the horizon. So a comet can be physically the same brightness yet appear 1 to 2 magnitudes fainter when clinging to 10 degrees altitude than it would at 50 degrees. Refraction lifts low objects by roughly a sun diameter near the horizon, but does not give you extra darkness. It can even smear faint features, making a soft coma softer and any tail less defined. The phase angle, the Sun-Object-Earth angle, often tracks with elongation. Small elongations can correspond to large phase angles near dusk or dawn, which sometimes enhances forward scattering from dust and can briefly help a dusty coma pop against the bright sky. while gas-dominated comae don't benefit as much. At opposition elongation near 180 degrees, the phase angle is small, improving surface brightness for solid bodies via the opposition surge, but providing no special boost for a diffuse low optical depth coma. Operationally, the elongation curve organises your calendar. Early in an apparition, when elongation grows past approximately 40 to 60 degrees, you get sustainable evening sessions with the object above 20 to 30 degrees altitude in nautical astronomical twilight. Around maximum elongation, you can ride deep night, plan long imaging runs, and vary your start times, which breaks the same coordinates feeling by sampling different local sidereal times. As elongation contracts on the outbound leg, your runs shorten again and drift toward repeated time slots, same half hour after sunset or before sunrise, so your telescope points into similar RA/DEC tiles with the same star patterns, reinforcing the impression of return. For planning, pair elongation with sun depression and altitude charts. A simple rule is that a faint, diffuse target needs sun less than or equal to -12 degrees, an object altitude greater than or equal to 25 degrees for comfortable imaging from typical suburban skies. If either number is worse, expect to push exposure time, gain and stacking, or accept that you're logging positions rather than making pretty pictures. In practice, you can squeeze more out of small elongation windows with a few tactics. Observe from a site with a low western or eastern horizon to maximise the minutes the object sits above your altitude cutoff. Pre-point the mount before twilight ends using plate solve and sync on a nearby bright star so you're ready the moment the object climbs into workable altitude. Use a luminance or clear filter to collect photons fast if your sky background and camera full well allow it, or a mild broadband LP filter if you fight sodium/LED glow, keeping in mind that strong filters can hurt a continuum-dominated target. Shorten subs when the sky is bright to avoid clipping, but increase the number of subs so the total integration still builds signal. Switch to comet rate guiding for a few minutes even in twilight so the object stays sharp while stars trail, making detection and centroiding easier against a bright background. Safety deserves a clear note. Small elongation can place your telescope dangerously near the sun. A go-to slew that grazes the solar limb without a proper solar filter can instantly damage optics and sensors. Use hard software limits and horizon masks when the sun is up, or just low the horizon, and never override them casually during dusk or dawn hunts. If you will be working at elongations under approximately 20 degrees, set a sun avoidance angle in your control software, or manually ensure any slew route stays on the night side of the horizon. For visual observers, low elongation comets are tougher than you might hope. The eye's contrast sensitivity drops in bright backgrounds, so a small binocular at nautical twilight will often beat a telescope at high power. For imagers, keep the histogram well clear of saturation and gather many short exposures, then reject shaky subs from the low altitude seeing and stack the rest with sigma clipping to tame twilight gradients. Elongation also interacts with lunar phase. A favourable elongation can be spoiled by a bright moon sharing the same sky quadrant. Doubling down on background brightness, plan around moonset or work in the opposite sky when possible, and remember that at small elongations the moon target separation is often modest, so even a waxing crescent can wash the scene. Moonlight raises the sky background by magnitudes, analogous to moving elongation closer in difficulty terms, even if the sun is far below the horizon. For prediction, watch ephemerides that list elongation alongside RA/DEC and altitude. Plotting elongation versus date gives a clean single curve picture of when your long, dark sessions will be possible, and when you'll be consigned to those repetitive edges of twilight. Combine that with rate of motion and phase angle plots to target the best compromises between darkness, altitude, and apparent movement. If you need to avoid the same window trap, deliberately shift your observing start by 20 to 40 minutes across successive nights to sample different hour angles. That one change moves the background star patterns, alters air mass and refraction effects, and makes the comet's progress more obvious in side-by-side frames. Logging the sun's depression, elongation, target altitude and sky brightness and use SQM readings with each session will help you understand why some nights felt identical while others revealed motion clearly. Finally, remember that elongation is geometry you can feel. As the number grows, your nights lengthen, your background darkens, and your flexibility increases. As the number shrinks, everything compresses: time, altitude, contrast, nudging you into consistent routines at the same wall clock minutes. And those consistent routines are exactly what create the repeating coordinates illusion. Mastering elongation means mastering when to look, how long you can look, and how to extract reliable measurements when you only have a sliver of sky between the glow of day and the hush of night. The sky has two clocks that run at slightly different speeds: the one we live by, the solar day, 24 hours from noon to noon, and the one the stars follow, the sidereal day, about 23 hours, 56 minutes, 4 seconds. Because the sidereal day is about 3 minutes 56 seconds shorter, the whole star pattern, including the right ascension line that runs through your south point, returns to the same position a little earlier each civil day. That small daily offset is the quiet engine behind the same place in the sky feeling. If you always step outside at say 2200 by your wall clock, you're actually observing at a later sidereal time each night, which means a different strip of right ascension is crossing your meridian, even if the clock says the same thing. After 1 week, the sidereal clock has drifted by roughly 27 to 28 minutes. After 15 days, it's about an hour. After a month, nearly 2 hours, and across a full year, the sidereal and solar clocks lap each other and come back into step. Local sidereal time, LST, is the key number that tells you which right ascension is on the local meridian right now. There's a simple relationship observers use all the time. When an object is due south and highest, its right ascension equals the LST. Equivalently, an object's hour angle is h equals LST minus RA. If h equals 0, it's on the meridian. If h is negative, the object is east and yet transit. If positive, it's west and past transit. Because LST advances about 360 degrees per sidereal day, not per solar day, h changes in a slightly different rhythm than your wristwatch suggests. That's why checking a comet at the same wall clock time can land you near the same hour angle for many nights in a row if your observing window is narrow. Making the motion feel sluggish or repetitive. A concrete example helps. Suppose 3i Atlas is near RA equals 12 hours and you start observing when your LST is approximately 11 hours 40 minutes on night 1, so the comet is 20 minutes before transit, h equals minus 0 hours 20 minutes. If you go out again exactly 24 hours later by civil time, your LST will be approximately 11 hours 44 minutes plus the 3 minutes 56 seconds sidereal lead, placing the meridian at approximately 11 hours 44 minutes on night 2 at that same clock time. Now the comet is about 16 minutes before transit. Keep that routine, and over 4 nights you'll still be checking it within a narrow band of hour angles around transit. The coordinates you jot down or the star pattern you see will look familiar, because you're repeatedly sampling the object near the same daily geometry, just a little earlier in sidereal terms each night. The effect is even stronger if your practical window is bounded by twilight or trees. You naturally pick a start time that fits the gap, and that small gap herds you back to similar LST values. There's a flip side that's useful. If you want to see change, observe at the same sidereal time instead of the same clock time. That means starting roughly 4 minutes earlier each civil day. Do that for a week and you'll be observing nearly half an hour earlier by the wall clock, but the Starfield will be in the same orientation, same LST, so any comet's shift against the stars will stand out because you've removed the nightly rotation of the sky from the comparison. You can feel this with a planisphere. Rotate the wheel 1 tick per day and you'll notice the same constellations arriving earlier. Lock the wheel at 1 sidereal time and the star map looks identical night after night, which is exactly the point of matching LST. Daylight saving time adds a human-made wrinkle. When clocks jump forward by 1 hour, your habitual 2200 suddenly corresponds to a different solar and sidereal circumstance. If you keep your old wall clock habit after the shift, you have effectively changed your observational hour angle by about an hour overnight, which can make a previously still object look like it suddenly started moving more or less between nights. Similarly, if your computer clock is a few minutes off UTC, your mount's internal conversion to LST will be off by the same amount, nudging you into slightly different hour angles than you think and complicating comparisons. Keeping devices synced to NTP and logging UTC to the minute helps keep your sidereal math honest. For practical planning, it helps to track three numbers together in your notes: LST at start, the object's RA, and the object's hour angle, H. If H hovers near the same small value each night, for example minus 0 hours 15 minutes to plus 0 hours 10 minutes, you're sampling the comet near transit repeatedly, so the backdrop will feel familiar, and the nightly displacement will project mostly east-west along RA lines. To vary the look, shift your start time by 20 to 40 minutes so H changes noticeably. If your window is constrained, say you can only observe in a 30-minute slice after the kids are asleep, alternate nights at that time with once-a-week sessions that are 1 hour earlier or later to break the pattern. It's also useful to understand how the sidereal offset maps to constellations through the seasons. Around late summer and early autumn evenings, the Milky Way high overhead drifts westward by about 1 degree per day relative to your constant clock time. Polaris sits close to fixed in the eyepiece, but everything else advances. If your comet rides through a dense star field, that daily westward drift combined with a small intrinsic comet motion can keep the same asterisms in view. By contrast, if you purposely observe at times separated by a sidereal hour, roughly 1 hour earlier civil time after 15 days, or 1 hour later civil time, before 15 days, the background rotates enough that you're forced to notice new landmarks and the comet's change of position. Imaging workflows respond to the two clocks too. If you always start stacking runs at the same civil time, your star alignment software will register frames taken at nearly the same sidereal orientation, and any mild field rotation in an Altaz setup will also be nearly the same, making inter-night comparisons look deceptively static. If you want motion to pop, try this. On night 1, shoot a short series centered at your usual time. On night 2, shoot another centered 30 to 40 minutes earlier by the clock. Plate solve both stacks, then blink them without star alignment first, so the whole star field appears at slightly different orientations, and then blink again with star alignment applied. The first blink shows the sidereal rotation difference. The second blink isolates the comet's true drift against a fixed star grid. Doing both makes it obvious what the sidereal clock contributed and what the comet contributed. There are a few handy rules of thumb to keep in your pocket. 1. The sky advances about 1 degree of right ascension per civil day at a fixed clock time, since 360 degrees over approximately 365 days, which is why a constellation rises roughly 4 minutes earlier each night. 2. Every 15 days at a fixed clock time corresponds to about 1 sidereal hour of drift. 3. At mid-latitudes, shifting your observing time by 30 minutes meaningfully changes the hour angle and air mass for most mid-evening targets, which changes both the look of the field and the contrast you'll get. 4. If you want to match the sky's orientation exactly a week later, start approximately 28 minutes earlier by the wall clock. The closer you match the LST, the cleaner your before/after subtraction will be. Finally, remember that telescopes and mounts live in this sidereal world by default. An equatorial mount tracks at the sidereal rate to keep the stars steady, not at the solar rate. If you feed it the wrong time or time zone, this idea of LST is wrong, and your go-to pointing to a given RA/DEC will be off by exactly the hour angle error you've introduced. That missed point can land you on a neighbouring star field that just happens to look like last night's, deepening the same coordinates impression. Keeping accurate time, noting LST, and intentionally varying your observing schedule are small, concrete steps that turn the invisible sidereal clock from a source of confusion into a tool you can use to reveal the comet's motion clearly. Ephemerides are simply schedules that tell you where an object will be in the sky at specific times, and they are the backbone of practical observing because they turn a moving three-dimensional orbit into the pointing numbers your mount or star chart needs. Each line of an ephemeris predicts a set of quantities for a chosen moment, typically right ascension and declination, RA/DEC, the object's distance from Earth and delta, and from the Sun, R, its solar elongation, the phase angle, how fast it's moving on the sky, arc seconds per minute, and often two position angles, one for the direction of motion and one for the Sun object line, useful for tail orientation. Most tables also include a predicted magnitude based on a brightness model, and many provide RA and DEC rates, DRA/D/T, DDEC/DT, that let a mount or guider track at the object's own speed instead of the sidereal rate. In practice, you choose a time grid, every 10 minutes, hourly, nightly, etc., pick a location, and generate topocentric ephemerids so they reflect your exact observing site rather than Earth's centre. This bakes in local parallax and makes the numbers match what your telescope actually sees. Under the hood, ephemerides come from propagating an orbit solution forward in time. That orbit is defined by elements, for example, perihelion distance q, eccentricity e, inclination I, longitude of ascending node omega, argument of perihelion omega, and time of perihelion passage TP, or by a state vector, position and velocity, in a consistent reference frame, often heliocentric or barycentric, referred to the J, 2000 equator and equinox. For interstellar objects, the eccentricity greater than 1 and the reciprocal semi-major axis 1/8 is negative, which flags an unbound hyperbolic path. Software integrates the trajectory while accounting for the Sun and planetary perturbations. Then, for a given observer position and time, it applies light time correction, where the object was when it emitted the photons you're receiving, aberration, apparent shift from Earth's motion, and precession/nutation to give you an apparent place on the celestial sphere. If you choose geocentric rather than topocentric, you'll get positions as seen from Earth's centre. Fine for planning, but topocentric will point your telescope better, especially for nearer or faster movers. Predicted brightness is always approximate. For comets and comet-like bodies, a common model is m approximately h plus 5 log delta plus n log r, where h is a reference magnitude, d is Earth distance in an AU, r is sun distance in AU, and n captures how activity scales with sunlight. N approximately 4 is a typical starting point for a moderately active comet, but the real value can differ a lot. That is why two reputable sources can list different magnitudes. They're using different H and N values derived from different data sets. Gas-rich comae can brighten differently than dust-rich ones, and phase angle effects, forward scattering near twilight, can boost apparent brightness temporarily, none of which a simple model fully captures. Treat the magnitude as a planning guide, not a promise. Rates matter more than many people expect. The line that says rate equals 0.8 per minute, PA equals 110 degrees, tells you how much the object smears during an exposure and in what direction. At 0.8 inches per minute, a 120-second sub will trail by approximately 1.6 inches, which may be hidden by seeing at coarse plate scales, but obvious at high resolution. If your software can accept RA/DEC rates, you can guide at the comet's rate so the comet stays round while the stars trail. If not, you can shorten subs and stack more of them. Or make a separate comet-aligned stack in post-processing. Position angle of motion also helps you verify you're on target. A measured streak or drift in roughly that direction is a good sanity check. Uncertainty is part of every ephemeris. Early after discovery, the observational arc, how many days of data, is short, and the solution comes with a covariance matrix that translates into an error ellipse on the sky for future dates. Good services visualize or publish an uncertainty value, or a 3-letter U parameter. High uncertainty means predicted positions can be off by arc minutes or more in just a few nights. As additional astrometry arrives from observatories worldwide, the fit improves. Residuals, observed minus computed, O minus C, shrink, and predicted positions stabilize. This is why stale ephemerides are dangerous. If you cached predictions on Monday and observe on Friday without refreshing, you might be pointing at the wrong patch, especially for a faint target. Make it a habit to regenerate ephemerides for your exact site before each session. Time scales and precision can trip people up. Orbit fits are often expressed in TDB/TT, relativistic/barycentric timescales, while your computer clock and mount run in UTC. Good tools convert for you, but if your system time is wrong by even a minute, a fast mover can be off by tens of arc seconds. Always sync your clock NTP and export tables with times in UTC, clearly labelled. Choose a step size that matches your needs. For imaging at short elongations, 5 to 15 minute steps make sense. For nightly planning, 1-hour steps may be adequate. Display enough digits. RA to 0.1 seconds, approximately 1.5 inches, and dec to 1 arc second helps you see real changes between nights. Rounding to the nearest arc minute will erase the very motion you're trying to measure. Reference frames and flavors of place matter. For pointing to night, ask for apparent topocentric ray/D/C of date, which include aberration and nutation and reflect your site. For archiving and comparing measurements across months or years, record J2000 mean RA/DEC plus the exact UTC time. If you publish astrometry, include uncertainties, plate scale and catalog used for plate solving and pass bands for photometry. If your path hugs the horizon, remember that atmospheric refraction won't change the catalog RA/DEC, but it will change where the image actually appears in your eyepiece by an arc, minute or more, near 10 degrees altitude. Good planetarium software will simulate apparent altitude including refraction. Don't ignore it when planning minimum elevation. Non-gravitational forces are a special case. If a comet is outgassing asymmetrically, it experiences a tiny rocket push that slightly alters the orbit. In those cases, fitters add empirical parameters A1, A2, A3 to absorb that acceleration. If those terms are present, ephemerides generated with them will diverge from ephemerides generated without them, and the with version will generally point better. Be aware of which model your source uses. Different sources can disagree for honest reasons. One service may propagate in a heliocentric frame with a certain planetary ephemeris and a fixed step integrator. Another may use a barycentric frame and a variable step integrator with general relativity terms. One might assume no outgassing, another includes it. One might output geocentric by default, another topocentric. None of this is wrong, but it does mean you should stick to one trusted pipeline per project, or at least compare with topocentric versus topocentric, apparent versus apparent, same epoch and timescale. If you switch tools mid-week, differences of a few arc seconds to arc minutes can appear, which is just enough to feel like the object returned to the same coordinates, when in fact your sources use different assumptions. Reading the line items efficiently helps. RA/DEC, where to point. Delta and R, how far it is from you and from the sun, useful for predicting brightness trends. Elongation, whether you're in deep night or squeezed into twilight. Phase angle, potential dust scattering boost and tail geometry. Rate and PA, exposure limits and tracking duration. Predicted mag, whether it's a camera target or a visual one. Add moon distance and altitude if your generator provides them. Moonlight and air mass will often dominate your success more than any other single factor. For workflow, a simple checklist keeps the numbers honest. 1. Set your observing site coordinates precisely, not just your city. Use lat long to at least 0.01 degrees. 2. Confirm your computer and mount times are synced to UTC and your time zone DST setting is correct. 3. Generate tupper-centric apparent ephemerides for your site for the exact session window, with steps of 5 to 15 minutes if you plan to shoot. 4. Export RA/DEC, RA/DEC rates, rate of motion, PA of motion, delta, R, elongation, phase, and predicted mag. 5. Load the list into your mount control or planning software. If available, enable tracking at object rate. 6. On target, plate solve to verify the field and sync the mount. 7. After the session, refresh ephemerides again before the next night, because new astrometry might have tightened the path. 2 last practical notes tie back to the same coordinates theme. First, avoid rounded displays and cached schedules. Show RA to at least 0.1 seconds and DEC to 1 arc second, and click Update on your Ephemeris pane each night so you don't unknowingly reuse the same coordinates. Second, log the exact Ephemeris source, model options, and generation time in your notes. If your experience diverges from the prediction, it looks still or it wasn't where expected, you can compare versions, check for non-gravitational updates, and decide whether the illusion came from identical planning coordinates or from real slow motion. Used this way, ephemerides are not just waypoints, they are the map, the clock, and the measuring stick that turn a faint interstellar visitor from a rumour in the noise into a traceable path you can follow night after night with confidence. Faintness starts with size and reflectivity. A small body reflects less sunlight because its surface area is small, and a dark surface returns even less because of low albedo. Double the diameter and you quadruple the reflecting area, halve the albedo and you halve the reflected light. Interstellar objects like this one are likely only a few hundred meters to a few kilometers across, and many are charcoal dark, so the baseline signal is weak before we even consider distance. Distance then squares the problem twice. Brightness falls off with the square of the distance from the Sun, less light received to reflect, and again with the square of the distance from Earth that reflected light spreads out before it reaches us. That's why the same object can be genuinely undetectable far out, become marginal near perihelion, and fade again quickly afterward. If surface ice is warm and sublime, gas drags dust from the surface and creates a coma that can boost total brightness, but that light is smeared over an extended cloud, so the surface brightness per square second, may still be low and hard to detect by eye. Whether it turns on with activity depends on composition, which ices are present and at what depths, temperature history and surface crust. A thin insulating crust can keep ices from venting, leaving the object mostly inert and therefore faint. Human eyes are not great at faint extended things, especially in light-polluted skies. Naked eye limiting magnitude in dark rural conditions is around +6, sometimes a bit better, but that's for a point-like star. A diffuse coma with the same total light can be invisible because the eye's contrast detection needs enough surface brightness above the sky background. Brightness per unit area is what matters for extended objects. City and suburban light pollution raises the sky background by multiple magnitudes, washing out low contrast fuzz. The moon acts like a light pollution switch in the sky. Even a half moon lifts the background dramatically, erasing faint coma and tails. Atmospheric extinction also dims objects at low altitude. At 2 air masses approximately 30 degrees altitude, expect on the order of a few tenths of a magnitude loss, worse in humid or dusty air. Seeing blurs starlight and spreads a faint coma even further, lowering peak intensity on the detector and making centroiding harder. All of this means that what a professional survey can detect with large apertures and tuned image processing may remain invisible to binoculars or small scopes under everyday conditions. Photometric models help set expectations, but they are approximations. A common comet formula, m approximately h plus 5 log delta plus n log r, says the total magnitude depends on Earth distance delta, Sun distance r, a reference magnitude h, and an activity exponent n that indicates how brightness responds to solar heating. For a quiet, rocky body with no coma, n behaves closer to 2 to 3, pure geometry and phase effects. For a dusty, alive coma, it can be 4 or higher near perihelion. Real comets wander from these tidy numbers. Outbursts, seasonal effects on a spinning irregular nucleus, or jet orientation can brighten or dim them relative to the model. Phase angle, Sun-object-Earth angle, matters as well. Forward scattering by dust near dusk/dawn geometries can give a temporary boost, while small phase angles near opposition don't help a diffuse coma much. This is why predictions from different sources disagree by several tenths, or whole magnitudes when activity is uncertain. Treat magnitude forecasts as a planning guide rather than a promise. Cameras make faint things possible by trading time and technique for photons. Signal-to-noise ratio, SNR, roughly scales with the square root of the number of collected photons. Stack n sub-exposures and random noise drops by square root n, so a barely there haze becomes measurable after enough integration. But there are constraints. If the comet moves at 0.8 inches per minute, a 3-minute sub smears 2.4 inches. At fine plate scales, that's noticeable and dilutes surface brightness further. You can shorten subs to keep trailing under your seeing disk, then stack more frames. You can also guide at the comet's rate so the coma stays sharp and stars trail. This helps centroiding and photometry, but makes pretty starfields trickier. Red noise and sky noise set a floor for sub-exposure length. Too short and you're dominated by red noise. Too long and you saturate the bright sky in twilight or near the moon. A fast optical system, low-F ratio, collects more light per unit time from extended objects. For comae and nebulae, F ratio matters more than aperture in terms of surface brightness on the detector, while aperture improves resolution and point source depth. Pixel scale should match seeing so you're not oversampling the blur and spreading precious photons across too many pixels. Flat fielding, bias/dark calibration, and careful background subtraction keep the faint glow from being mistaken for gradients. Aperture and filter choices influence detectability. Broadband luminance, or no filter, maximizes photon throughput for a continuum-dominated coma. Mild broadband light pollution filters can help by trimming sky glow, but aggressive narrowband filters, unless you are specifically targeting emission bands like CN or C2, often hurt total signal. If gas emissions are present, a narrowband comet filter can isolate them for science, but won't necessarily make the comet look brighter visually. In twilight or at small solar elongation, shorter subs help avoid clipping the background, and more total subs maintain SNR. In moonlight, plan around moonset or target when the moon-comet separation is large. Even 60 to 90 degree separation can make the difference between a detectable haze and a lost target. Not all faintness is created equal. A small inert interstellar fragment may peak as a featureless point-like speck with a stellar profile, in which case telescopes treat it like a dim asteroid, and it can punch above its size because point sources are easier to detect than extended smudges. By contrast, a weakly active coma with very low surface brightness can have a deceptively bright, integrated magnitude that never materializes for your eyes because the light is spread thin. This is why observers share both total magnitude and coma diameter estimates, and why surface brightness maps or isophotes are useful when comparing experiences from different sites. Quantitative measures help separate too faint to see from faint but measurable. The AFR parameter is a commonly used dust proxy that, while imperfect, gives a distance-independent sense of dust production. Rising AFR hints that a coma could firm up visually later, while flat or falling AFOS suggests it will remain a photographic challenge. Photometry should be done on linear, calibrated images with consistent apertures and sky annuli to avoid fooling yourself with stretch-dependent impressions. When logging, note sky quality, e.g. SQM readings, air mass, moon phase elongation, sub-exposure length, plate scale, and whether you tracked at sidereal or comet rate. Those details explain why one night's invisible becomes another night's obvious, even though the object itself changed little. Finally, there's the psychological side of faintness. Expectations are set by splashy historical comets with bright tails and obvious comi, but most small visitors, especially fast interstellar ones, do not perform that way. They are subtle targets that reward patience, precise timing, careful processing, and realistic goals. If the plan is a public showpiece, faintness is frustrating. If the plan is measurement and quiet discovery, faintness is an invitation to hone technique. In practice, that means choosing darker sites when possible, observing at larger solar elongations for deeper darkness and higher altitude, working with accurate ephemerides so precious minutes aren't lost to slewing, and embracing stacks long enough to lift the signal above the noise. When you do, the object that seemed absent becomes a faint, steady presence, and its dimness turns from a disappointment into a lesson in how much is still visible when you meet the sky on its terms. When people ask if 3i Atlas is dangerous, they're really asking three different questions. Could it hit Earth? Could it disturb Earth in some other way? Tides, radiation, space weather? And could watching it be risky for me or my equipment? The calm, factual answers are no, no, and only if you ignore ordinary observing safety. Start with impact risk. For any newly found object, astronomers compute its orbit and then compare that path to Earth's path, using a metric called the Minimum Orbit Intersection Distance, MOID. A very small MOID can mean a potential for close approaches over long timescales if the timing lines up, while a large MOID makes close approaches impossible. Interstellar objects like this one follow unbound hyperbolic orbits, eccentricity greater than 1, which already tells you they're just passing through once, when the best fit trajectory and its uncertainty region, the error ellipse projected forward, are far from Earth at the relevant times. We can say there is no credible collision geometry. Early after discovery, orbit uncertainties are larger, so teams update solutions as new measurements arrive, shrinking that uncertainty tube. If Earth were inside the tube, the risk scales used by planetary defense, the Torino scale and Palermo technical scale, would reflect that with non-zero values. But when solutions stay well clear of Earth, those scales remain at the safe end and the object quietly ages out of public watch lists. Distance matters for more than just miss or hit. A distant flyby means no meaningful gravitational effect on the Earth-Moon system. Gravitational tides fall off with the cube of distance, so unless an object is both massive and extremely close, think Moon close, the tidal influence is negligible. A small interstellar fragment many millions of kilometers away simply can't tug oceans, trigger quakes, or bend orbits. The numbers are too small by orders of magnitude. Electromagnetic effects aren't a concern either. There is no mechanism by which a dark, inert body amplifies solar radiation or alters Earth's magnetosphere. Space weather events come from the sun, flares, coronal mass ejections, and from high-energy cosmic particles, not from passing rocks. If the object becomes slightly active near the sun and releases dust, that dust expands into an extremely diffuse cloud along the orbit. The column densities are so low that even if a filament crossed Earth's path years later, the effect would be limited to a few extra meteors. Pretty streaks in the sky, not hazards. It's useful to know how scientists turn "we think it's safe" into "we know it's safe." Each observation yields a time-stamped position against background stars. A fit to many such points produces an orbit and a covariance matrix that quantifies uncertainty. That combination lets you propagate not just a single path, but a cloud of plausible paths into the future and measure how far that cloud stays from Earth and the Moon at each date. If planetary perturbations could, in principle, bend the path toward us, that would show up as portions of the cloud drifting into small keyholes, which are narrow regions near a planet where a tiny deflection leads to a later close approach. For fast hyperbolic visitors, the time spent in any keyhole is brief, the required alignment is razor thin, and the inbound and outbound speeds are high enough that significant deflection is extraordinarily unlikely. Practically the propagated cloud doesn't intersect keyholes that matter for Earth. Meanwhile, survey networks Atlas, Pan-STARRS, ZTF, Catalina and others keep collecting data, and global centres recompute the orbit daily, so if anything surprising showed up, it would be reflected immediately in updated elements, uncertainty, and risk scales. Close approach anxiety often comes from misreading sky maps. A chart might show the object near a constellation or passing a bright planet, but that's a line of sight projection on the sky dome, not a physical neighbourhood in space. On the chart, two things can look adjacent while being millions of kilometres apart in 3 dimensions. The values to watch for actual proximity are the geocentric distance delta in astronomical units or kilometres, and the MOID, not a picture with overlapping symbols. Similarly, faster apparent motion near perihelion can look dramatic on camera frames but says nothing about danger. It's simply geometry. Closer objects sweep past background stars faster even at the same physical speed, the same way a nearby bird crosses your window faster than a distant plane. Some people worry about capture, the idea that the sun or a planet could grab an interstellar body and bring it into a bound orbit that later intersects Earth. Capture without dissipation is nearly impossible. To bind an incoming hyperbolic object, it would need to lose enough energy to drop below escape speed. Gravity alone can't remove energy, it can only exchange it, which is why gravitational assists change direction and speed relative to the sun but conserve total energy when you include the planet. Real capture requires a dissipative process like passing through a deep atmosphere, or an exquisitely tuned 3-body interaction that robs just the right amount of energy. With a small, fast object and no thick atmospheres in the neighbourhood of its path, capture is not a realistic outcome. The expected story is a single in and out passage. If you're thinking about personal safety while observing, the practical risks are the ordinary ones of nighttime fieldwork, not cosmic hazards. Protect your eyes and gear by respecting the sun. Never slew near the sun without hard software limits or a physical solar filter properly installed. A single accidental exposure can destroy a sensor or worse. In evening hunts at small solar elongation, set conservative sun avoidance angles and horizon limits in your mount control, and double-check slews. Manage your environment, use red lights to preserve night vision, but keep them dim to avoid tripping hazards. Tell someone where you'll be, pack warm layers, be cautious on dark roads when you're tired. Avoid using high-power green lasers near airports and be aware of local regulations. For the gear, keep dew control running so optics don't haze over and tempt you into unnecessary fiddling in the dark. A dewy corrector plate erases faint targets faster than any cosmic variable. For mental peace, it helps to keep scale in mind. Small near-Earth asteroids a few tens of meters across pass within the orbit of the Moon, several times per month. They are tracked, catalogued, and almost always pose no risk. They also go essentially unnoticed by the public because they are routine. An interstellar object following a safe, measured path is even less of a concern. It's farther away, typically smaller in apparent size and moving on a one-time arc that doesn't weave through Earth's orbital neighbourhood again. The parts of planetary defence that warrant attention: survey completeness for kilometre-class objects, impact exercises, deflection technology, are global, long-term efforts that do not hinge on a single faint visitor. Finally, it's worth knowing how safety appears in the numbers you might see shared between observers. A missed distance might be quoted in lunar distances, LD, or astronomical units, AU. Values of many LDSs or a comfortable fraction of an AU mean far. The relative speed at closest approach will be high. Interstellar V infinity is non-zero, so the duration of any close geometry is brief, measured in hours or a day, not weeks. Uncertainty shrinkage over time is visible as ephemeris from different days converging to the same coordinates rather than diverging. Convergence is the fingerprint of a stable solution. and if you ever see someone claim it's heading straight at us based on a sky chart arrow, check the data table instead. RA/DEC are where to point. Delta is how far and the rest is projection. With that frame, the right kind of calm sets in. This is a distant passerby, the math is clean, the tracking is routine, and the only practical danger is forgetting that a low sun can fry a camera while you're chasing a faint speck at the edges of twilight. A hyperbolic orbit is an in-once, out-once path. In gravity terms, it means the object's total energy with respect to the sun is positive, its orbital eccentricity is greater than 1, and there is a non-zero excess speed far from the sun, often written v infinity, that the sun's gravity cannot erase. Picture two straight lines that never meet. Those are the inbound and outbound asymptotes of the path, and the sun gently bends the inbound line into the outbound line by a fixed deflection angle before letting the object go. The closer the pass and the slower the arrival, the larger the bend. The farther and faster, the smaller the bend. Crucially, there is no loop, no capture, and no future reappearance built into such a trajectory. Kepler's laws still describe the shape at each instant, but it's the energy sign that tells the story. Negative for bound ellipses, 0 for the parabolic knife edge between bound and unbound, and positive for hyperbolas that never close. This is different in spirit from a periodic comet on an ellipse. A periodic comet trades distance for speed over and over, faster at perihelion, slower at aphelion, repeating with a well-defined period. Its coming back is baked into the geometry. A hyperbolic visitor speeds up as it falls inward, reaches a single perihelion, then decelerates forever as it leaves, and because v infinity greater than 0, the slowdown never reaches a stop. If you could ride along very far from the sun, you would see the object asymptotically settle into straight flight at v infinity, carrying on into interstellar space. That is why returns to the same coordinates is an observing artifact born of schedules and sky grids, not a physical return. The path itself has no second act within the solar system. Mathematically, you can think of the hyperbola's tightness around the sun as controlled by two knobs. The impact parameter, how closely the inbound line would pass the sun if there were no gravity, and the inbound speed. Gravity bends the track in a predictable way. In scattering language, the sun is a point mass deflector, and the turning angle falls as the inbound speed grows, or the missed distance increases. The hyperbola's closest approach is perihelion, and if you describe the shape in the same orbital element language used for ellipses, you would list a perihelion distance q, an eccentricity e greater than 1, an inclination I, tilt with respect to the ecliptic, and orientation angles omega and omega, locating the line of nodes and the perihelion direction in space. Although semi-major axis A is negative for a hyperbola, the combination 1 over A is still useful. It is proportional to the specific orbital energy. The Laplace-Runge-Lenz vector, which points toward perihelion and has a magnitude equal to E, is another way to see that the path has a fixed orientation and shape under pure two-body gravity with no looping back. Observationally, hyperbolic motion has a calm one-time rhythm. Far out, apparent motion against the stars is slow and the object is faint. As it approaches, both brightness and sky speed generally increase. Near perihelion, the apparent motion can be the fastest you'll record, especially if the geometry makes the object's path cross large angles on the sky in a short number of days. After perihelion, the speed against the stars steadily drops as distance grows. The light curve, the way brightness changes over time, follows distance and activity. If it's inert, the brightening and fading are governed mostly by 1 over a squared and 1 over delta squared geometry. If it's weakly active, solar heating can add a steeper ramp near perihelion and a slower fade afterward. What you never see in a hyperbola is the brightness and motion resetting for another go-round. There is no second perihelion, no periodic timetable to hang a next apparition on. There are two flavours of hyperbolic comets worth separating. one is truly interstellar. It arrives from outside the Sun's family, already on an unbound path with E greater than 1 before any planetary encounters, and it leaves with a greater than 1. The other is a formerly bound comet that got kicked by a close interaction with a giant planet and was flung onto a hyperbola. Its E becomes greater than 1 after the encounter. Both are unbound afterward, but only the first proves an origin beyond the solar system. In practice, you can tell them apart by solving the original orbit before planetary perturbations. Interstellar objects have strongly hyperbolic original solutions and significant V-infinity, not just barely above 1.00 in eccentricity. That distinction matters scientifically, but doesn't change the headline for observers. The outbound leg is a goodbye either way. Because a hyperbola is unbound, capture is not on the menu unless some dissipative process removes energy. Gravity alone conserves energy in these encounters. Planets can redirect and slightly adjust speeds in the Sun's frame through gravitational assists, but they won't magically turn a fast interstellar track into a closed ellipse without an additional brake. Thick atmospheres can act as a brake, or aero capture, but there is no thick atmosphere near a realistic pass for a small faint visitor, and the alignment for a three-body energy exchange strong enough to bind a small object is fantastically specific. The expected outcome remains a single pass. Mapping that path to our night-to-night experience involves coordinate frames. The osculating orbit quoted by services is expressed in a clean inertial frame, often heliocentric or barycentric, referred to the J2000 equator and equinox. From there, predictions transform the object's state to topocentric apparent RA/DEC for your site at a given UTC, applying light time, aberration, precession, and nutation. This chain never produces a true repeat of positions for a hyperbola. At most, if you sample at the same wall clock minutes in narrow dusk or dawn windows and round heavily, successive entries in your log can look similar. Refreshing ephemerides, using arc-second precision, and plate-solving images reveal the steady one-way drift that the underlying hyperbola guarantees. On the physics side, it's instructive to look at conserved quantities. Specific angular momentum is constant in the two-body sun-object problem, so the motion stays in a single plane, the orbital plane, throughout. Specific orbital energy stays positive and constant in that same idealization, which is why the object never transitions to a bound state. The shape parameter E and the perihelion distance Q are fixed, absent outgassing forces. If gentle non-gravitational accelerations exist, jets acting, like tiny thrusters, they are folded into refined orbit models as small parameters and shift the predicted track by arcs, seconds, to arc minutes over weeks, not by degrees. These tweaks can alter predicted timing and sky position slightly, but do not convert an unbound curve into a bound one. The idea that a hyperbola is a one-note song undersells how much science it carries. Spectra taken along the way can reveal what ices and dust it carries. Astrometry across the inbound and outbound legs tightens our estimate of V-infinity and the inbound radiant, the direction in the sky from which the object approached before the sun's deflection. That radiant links to the broader galactic velocity distribution of small bodies and, in some cases, to local standard of rest comparisons, helping scientists understand how such fragments wander between stars. Photometry can track whether activity turns on near perihelion and how quickly it shuts off afterward, giving clues to surface crusts and volatile content. All of this is framed by the certainty that the path won't repeat here, which focuses attention on making the most of the single available arc. For planning, the hyperbolic shape has practical consequences. There's typically one best window for deep imaging when elongation, altitude and brightness cooperate. Before that, it's too far and faint. Afterward, it fades and sinks toward the horizon at inconvenient hours. Rate of motion curves often show a single smooth peak around the time geometry is most favourable. Tracking strategies and sub-exposure lengths can be planned around that, with shorter subs and comet rate guiding near the peak and longer subs at the slow ends. Tail orientation, a vector roughly away from the Sun, will sweep through position angles as the Sun-object-Earth geometry evolves once. Annotating images with the predicted anti-solar direction makes it easier to decide whether a subtle extension is real dust or just background noise. If you like analogies, think of bound orbits as tracks on a circular train line and hyperbolic passes as express trains on a straight main line through town. The express does curve near the central station, but it never loops into the circle line, and it doesn't come back tomorrow on the same schedule. You can plan to see it once on its way in, maybe again as it departs from the far platform, and then it's gone, leaving behind your photographs, your measurements, and an updated timetable proving that what looked like a gentle arc on a map was, at heart, a straight journey that only bowed briefly to the Sun before continuing into the wider night. Not all observers watch from Earth. As 3i Atlas sweeps past the Sun, other vantage points, Mars orbiters, heliophysics probes near the Sun, and space telescopes away from Earth can see geometry that is hidden from backyard observers, and those extra eyes change what we can measure. Start with simple parallax, put two observers far apart and measure the object against background stars at the same time, and you get a long, clean baseline that tightens the orbit. Earth and Mars can be tens to hundreds of millions of kilometers apart. That separation turns tiny uncertainties in right ascension and declination to big leverage on distance and direction, even if each platform's astrometry is only modestly prepidor. The long triangle slashes the tube of possible futures, clarifying V infinity, the inbound radiant, and any small non-gravitational drifts. Timing matters here. Simultaneous or near-simultaneous images let you solve for lines of sight that intersect in space, whereas single-site night-to-night tracking mixes true motion with Earth's own changing vantage point. Mars assets sit in a different sky than we do, with different sun angles and background fields. A comet that hugs our evening twilight might sit higher and darker for an orbiter over Mars because the planet's rotation and the Sun-Comet-Mars geometry line up more kindly. That can mean longer exposures, higher altitude above the local horizon, and lower air mass equivalents through a thinner atmosphere. Mars has an atmosphere, but for orbiters taking space-looking images, there's no air mass to fight. Mars also gives independent apparent motion vectors. From Earth, the object may seem to slide east-west against one star field, while from Mars it crosses in a different direction or speed. Fit both, and you separate real 3D motion from projection effects cleanly. Even coarse measurements like it moved X arc seconds over Y hours are powerful when the baselines are that long. Solar watching probes supply a wholly different benefit. They live where elongation is small and twilight doesn't exist. Coronagraphs and wide-field heliospheric imagers stare near the Sun all the time, so a faint, dust-shedding object can be visible in their fields when ground observers are blinded by daylight. If activity turns on near perihelion, those instruments can see dust streams forming and evolving on timescales of hours to days. Because they often observe in broad visible bands optimized for faint Thomson-scattered sunlight from the solar wind, a small coma or tail can stand out as a low-surface brightness structure even when it's hopeless from the ground. The spacecraft orbits help too. A probe that trails or leads Earth in its orbit views the same object at a different phase angle, sometimes catching forward scattered dust, which briefly makes the coma and tail brighter per unit area than we see from Earth. Heliophysics imagers have another quiet advantage. They produce high-cadence sequences. A daily or sub-daily movie makes subtle changes in morphology obvious, lets teams measure tail position angles precisely, and pinpoints when any outburst started. Information that feeds back into thermal models and composition guesses. Infrared space telescopes fill in what reflected light hides. In the thermal infrared, you measure the object's heat rather than its sunlight, which, combined with reflected light brightness, lets you break the size albedo degeneracy. A dark, large body and a small, bright body can look the same in visible light. They don't in the mid-IR. If an IR telescope can track moving targets at the object's apparent rate, and it sits at a thermally stable vantage point away from Earth's glow, it can integrate for long stretches without atmospheric noise. Low-resolution spectra across near-IR bands can reveal ices and organics in emission or absorption, while mid-IR can constrain grain sizes and dust temperatures in the coma. Those spectra matched to the inbound/outbound parts of the path tell you whether volatiles turn on and shut down symmetrically, or whether one hemisphere dominates because of spin axis orientation and seasonal lighting. Space telescopes have strict pointing constraints that often differ from your backyard gear. Many cannot look too close to the Sun, a solar elongation avoidance zone, and have upper limits on how fast a target can appear to move across their detectors. That means a hyperbolic visitor might be observable for only a narrow window when its rate drops below the tracking threshold and its sun angle lies within allowed bounds. Planning teams therefore compute visibility windows that include solar elongation limits, Earth/Moon avoidance angles, the spacecraft's own thermal constraints, and guide star availability for non-sidereal tracking. Inside the window, they choose their instrument modes: spectroscopy versus imaging, slitless versus slit, short versus long wavelengths that match the object's brightness and rate so that trailing stays under control. Because each exposure is precious, they often pair deep integrations with short finder frames to keep the moving target centered. Mars-orbiting cameras can help in ways that are not obvious. High-resolution images designed for mapping the Martian surface sometimes look outward for calibration or planetary events. If they can be tasked to a moving speck, even a handful of detections provide parallax points far from Earth, and a coarse light curve free from telluric absorption and moonlight. Transmission through a spacecraft's optics is stable and repeatable, so relative photometry, brightness changes from one image to the next, is often cleaner than from ground observatories with changing weather and air mass. MAVEN-like instruments sensitive to ultraviolet emissions can, in principle, detect gas species that are swamped by sky background from Earth, offering clues about outgassing even when dust signatures are weak. If the geometry ever produced a close pass by Mars, the planet's fleet could pivot to a dedicated campaign, as has been done for comets before. Imaging, spectra, and even in situ dust measurements if a tenuous stream brushed the upper atmosphere. But even without a close pass, the mere existence of a second deep space vantage is gold for orbit fitting. Triangulation doesn't stop at 2 points. Add a heliospheric imager from a sun-leading orbit to Earth and Mars, and you have a 3-site network. Fit those lines of sight and you solve for the object's 3D location and velocity more directly than any single site can manage, especially over short arcs. That reduces covariance couplings, cases where distance and direction errors masquerade as one another, and gives a sharper inbound radiant that you can compare with galactic kinematics. A well-defined radiant lets dynamicists ask whether the object's motion resembles the local standard of rest, a nearby stellar stream, or simply the broad background of ejected planetesimals, which in turn informs how common such visitors should be. Occultations, moments when the object passes directly in front of a star, are another place where distributed observers shine. Predicting them requires extremely accurate orbits, but if the Ephemeris is good enough, a network spread around the solar system, not just around Earth, can chase a faint dip in starlight at different chords. Even one clean chord limits size. Multiple chords bound shape and can expose a coma so thin you'd otherwise miss it. A Mars-side chord combined with Earth-side chords turns the silhouette into a true 3D constraint rather than a single projected outline. Spacecraft cameras have stable photometric baselines and no atmospheric scintillation, which improves detection thresholds for millimag-level dips. Not every technique works for a distant small interstellar body. Planetary radar thrives on nearby slow targets. At tens of millions of kilometers with high relative speed, signal-to-noise plummets and round-trip light times eat practical transmit windows. In-situ sampling isn't realistic on Discovery timescales. Even the most agile mission concepts need lead time and favourable geometry that hyperbolic visitors rarely offer. But dust and gas detectors on inner heliosphere probes can sniff the environment for compositional hints if a tail outflow crosses their orbits, and plasma instruments can study how cometary ions mingle with the solar wind even when the nucleus is just a dot in the camera. Those at-hand measurements anchor models of how dust grains charge, how they respond to radiation pressure, and how tails curve in different heliocentric electric and magnetic environments. Data from these platforms flow through different pipelines but converge in the same places. Orbit servers and small body databases that fuse astrometry, photometry, and spectra. A Mars side measurement might arrive as a handful of plate-solved centroids. A heliospheric imager might contribute position angles of a dust feature and rates derived from time-sequenced frames. An infrared telescope might deliver a thermal flux and colour temperature. Folded together, they tell a coherent story. How fast the object came in, which direction it came from, how its brightness evolved, what ices and dust it carried, how the dust responded to sunlight near perihelion, and whether any tiny non-gravitational push is present. Because the path is unbound, there's only one chance to get these pieces. The value of off-Earth perspectives is that they open observing windows when Earths are closed, and if they turn a single narrow view into a multi-angle reconstruction that's robust against the illusions of repeated coordinates, twilight constraints, and Starfield crowding. In practice, that means a calm division of labour. Earth-based telescopes handle deep, high-resolution frames when elongation is generous. Mars and other planets contribute parallax and alternative geometries. Heliophysics probers catch the perihelion side drama near the Sun, and infrared observatories convert faint heat into firm size and albedo estimates, together building the most complete picture possible of a fast visitor that will not pass this way again. What we learn from a fast, faint visitor divides into a few big buckets: motion, light, heat, gas, dust, and each bucket answers a different kind of question. The motion part looks deceptively simple, but it is foundational. Precise astrometry night after night fixes the inbound direction of the radiant, and the excess speed at infinity, v infinity. From those two numbers you learn how the object fits into the local flow of stars and small bodies in our part of the galaxy, and whether its path is consistent with a random interstellar wanderer or hints at a specific stellar stream. As the orbit solution tightens, even tiny departures from a pure gravity track, non-gravitational accelerations from outgassing, show up as milliarc-second nudges. Fitting those with standard A1/A2/A3 parameters tells you whether material is really leaving the surface and in which preferred directions, which in turn constrains the spin state and where active areas might sit on the nucleus. If the fit stubbornly prefers zero non-grav terms, that argues for an inert, rock-dominated body. If small but significant terms appear, the case for ices strengthens. Light, meanwhile, carries fingerprints in both colour and polarisation. Broadband colours, for example G-R, R-I, place the object on well-mapped trends for comets and asteroids. Many cometary comae are slightly reddened relative to the Sun. A neutral or very red slope compared to solar system comets could suggest different grain size distributions or surface processing histories. Polarimetry measures how scattered sunlight is polarized by dust. The curve of polarization versus phase angle, the Sun-object-Earth angle, is a powerful discriminator of grain porosity and size. A polarization curve that deviates from typical comet curves would point to a different dust microphysics, fluffier aggregates, more compact grains, or unusual compositions. Because phase angle evolves smoothly along the inbound and outbound legs, repeated measurements trace out the full curve rather than a single snapshot, turning a quick pass into a rich diagnostic of dust texture. Thermal infrared data breaks a classic degeneracy. In reflected light, a small bright body and a larger dark one can look the same. Mid-IR flux depends on surface temperature and emitting area, so pairing a thermal measurement with visible brightness lets you solve simultaneously for effective size and geometric albedo using standard thermal models, NEATM and its cousins. If there is a detectable coma, the thermal slope can also hint at grain sizes. Small grains heat and cool differently than large grains. And multi-band IR photometry constrains dust temperatures and thus distances from the nucleus where grains dominate. A very low albedo paired with a modest size would align with many dormant or spent comet nuclei. A higher albedo could suggest fresher ice or reflective dust mantles. Spectroscopy is where composition moves from guess to measurement. Gas species produce narrow emission bands. In the optical, that often means CN, C2, C3, NH, and OI lines from dissociation products. In the near UV blue, CN is a workhorse tracer. In the near IR, bands of H2O, CO, and CO2 can reveal which volatiles drive activity at a given distance from the Sun. Measuring production rates, QCN, QH2O, QCO, and QCO2, across time gives an activity ledger. When does the object turn on, which gases led, which lag, and how quickly does it shut down after perihelion? Ratios like C2 over Cn, CO2 over H2O, and CO over H2O situate the object among known families of comets. Being interstellar, it might fall outside familiar clusters, which would be a discovery in itself. High-resolution spectra can push further to isotopes. D over H in water, 12C over 13C, 14N over 15N, each a subtle thermometer of the conditions where the ice is formed. A D/H ratio, markedly different from solar system comets, would argue that planet-forming disks across the galaxy can freeze water under different temperatures and histories than our own. If no gas lines are seen, that result is also valuable. It sets strict upper limits on volatiles and strengthens the case for a devolatilized surface crust or for a small body whose ices are shielded or absent. Dust morphology encodes dynamics in slow motion. A dust coma and tail are not shapeless. Their curvature and width reflect a balance of the initial launch speeds, solar gravity, and radiation pressure. Analysts map this with syndynes and synchrones. Curves of constant beta, the ratio of radiation pressure to gravity, tied to grain size, and lines for equal emission times. Fitting those patterns across several nights yields both the grain size distribution and the timing of emission bursts. If synchronic features point back to a specific date, that may flag an outburst. Matching beta values translate to dominant grain sizes microns across, tens of microns or larger. Combined with photometry, you can derive AFR, a distance-independent proxy for dust production. Its rise or fall across the apparition indicates whether the dust engine is steady, surging, or shutting down. The antisolar tail versus orbit-aligned dust trail distinction also matters. The former clues recent activity, the latter traces larger, older grains that lag the orbit and can persist long after gas activity fades. Light curves, the small periodic wiggles in brightness as the body rotates, add another layer. A double-peaked light curve suggests an elongated shape. The amplitude constrains the axis ratio, and the period pins the spin rate. If measurements inbound and outbound show the same period but a changing amplitude, that can indicate changing viewing geometry. We saw the side on one leg and a more pole-on view on the other. If the period appears to drift slightly and gas is present, non-uniform jets can exert tiny torques that alter rotation state over weeks. Even a small torque is detectable when the time series is dense. With sparse photometry from multiple longitudes, convex shape inversion methods can sketch a coarse 3D silhouette. Crude for such a faint object, but often enough to decide whether you're watching a blocky nugget, a more spheroidal fragment, or something unusually elongated. All the while, the evolving phase angle offers a built-in experiment in scattering. At small phase angles, some surfaces exhibit an opposition surge, a non-linear brightening tied to shadow, hiding, and coherent backscatter. A coma with fine dust shows that surge differently than a bare nucleus. tracking how total brightness departs from a pure 1 over A squared times 1 over delta squared law, as phase changes lets you separate nucleus-dominated and coma-dominated regimes, and, with enough bands, measure a phase function that you can compare directly to comet nuclei, D-type asteroids and Trojan populations. A match hints at shared surface physics, a mismatch flags genuinely different regolith or mantle properties. Even non-detections advance the story. A night with no gas lines to a given sensitivity sets upper limits on Q values that tighten thermal models. A failure to see a tail at a phase angle that should favour forward scattering limits the abundance of small grains. A flat polarisation signal within errors rules out extreme porosity cases. Each limit carves away parts of parameter space until the remaining combinations of size, albedo, grain sizes, and volatile content form a self-consistent picture. Because the object is unbound and time is short, these limits accumulate quickly into a surprisingly sharp portrait despite the brief visit. Cross comparisons make the learning cumulative. Place its albedo size point on a plot with previous interstellar visitors, and with inner and outer solar system comets. Add its colour to the cloud of small body spectral slopes. Drop its polarisation curve onto the family of comet curves. Overlay its AFR timeline with distance to see whether dust scales in a familiar way with R, and compare any isotopic constraints with the spread seen in Oort cloud comets and Jupiter family comets. Agreement in several spaces suggests that planet-forming chemistry and dust physics are robust across systems. Outliers suggest diversity, different disk temperatures, mixing, irradiation, or processing before ejection into interstellar space. Either answer is scientifically rich. Sameness argues for universality, difference argues for variety we can measure. Finally, the methods we practice while it is here become part of the toolkit for whatever comes next. Rapid response scheduling, non-sidereal tracking at high rates, plate-solved astrometry with consistent catalogues, synchronized multilongitudinal photometry, polarimetry and narrow twilight windows, infrared follow-ups at the edge of tracking limits. Each technique gets refined under real pressure. Databases and pipelines learn to ingest multi-platform data. Ground-based spectra, space-based thermal points, heliospheric imager position angles, perhaps even a Mars-side parallax tie. The result is not just a dossier on a single traveller, but a better system for turning the next faint streak into physics. How fast it came, what it's made of, how its dust behaves, how its ices respond to sunlight, and what that says about the worlds being built and flung away around distant suns. There is a quiet kind of awe that arrives when you realise you are watching something that does not belong to our sun, and that the light now touching your retina left an object that has been travelling since before your language, your town, your habits existed. Standing under that thought, your tools feel simple. Mount, optics, a red lamp, a small notebook, but they are enough to stitch you to a path that crosses the whole idea of home. You look up, and even if the comet or fragment or snowdark stone is only a softened dot on your screen, the act of following it steadies the mind. Set the coordinates, plate solve, expose, check the histogram, breathe. The ritual is ordinary and precise, and in the middle of it you notice that the wind has a different temperature after midnight, that the dew band hums like a distant insect, while your breath becomes a tiny weather system in the cone of your light. The object itself does not perform for you. It glides. It refuses spectacle. It offers what it has. A faint rise in brightness as geometry improves, a nudge in the centroid from one night to the next, perhaps a hint of dust if sunlight teases anything loose, and in this restraint it teaches you to widen your idea of beauty to include what is barely there. You begin to measure yourself by smaller units, arc seconds, millimagnitudes, minutes of sidereal drift. You learn that patience is a form of attention, and attention is a form of respect. Noise falls when you stack enough frames. Doubts fall when you stack enough nights. The bright patterns in the Starfield that used to steal your eye become instruments, anchors you use deliberately, not traps that bind you to sameness. And in choosing when to start, how long to stay, and where to point, you discover that the sky is not a movie, but a conversation that waits for you to ask better questions. What is your rate? You ask the faint smudge. What is your colour? Do you carry dust that scatters forward at dawn? Do you stir when warmed, or pass in silence? Every answer is modest, and somehow that makes it feel larger, as if the universe has decided to speak softly, so you have to lean closer. Out on the edge of the field, the ordinary world continues. Trucks hiss on a far road, a neighbour's porch light clicks, a fox decides the night belongs to it, and none of that cancels what you are doing. You are counting photons from a body that began life under another star. Between one exposure and the next, your sense of distance changes scale. Millions of kilometres become near, hours become fast, a tenth of a magnitude becomes dramatic. And the longer you stay with it, the more your own breathing aligns with the sky's slower clock. Seasons of the mind appear, the early anxiety season when you wonder if you'll find it, the relief season when the plate solve draws a tiny circle around exactly the right spec, the curiosity season when you vary settings and chase morphology no one else will notice, the gratitude season when a clear window opens after a week of clouds and everything just works. You come to understand that humility is a technology. It lets you accept the limits of your sight, your seeing, your gear, your time, and then make the most of them. You stop arguing with the sky and start learning from it. Twilight stops being a nuisance and becomes a teacher of gradients. Moonlight becomes a lesson in contrast and patience. Small elongations teach safety and planning. Crowded starfields teach you to measure rather than assume. In each of these, the visitor is not the only subject, you are too, and the experiment is about what happens to a human attention when it meets something that will not bend to it. If the object remains faint, you practice seeing faintly. If it wakes a little, you practice not chasing promises it never made. Either way, when you pack up, the world is quieter in a way that lasts until morning. The camera saves a row of files whose names mean nothing to anyone else, but they are a map of a unique crossing. The night the comet stood at that RA/DEC beside the shallow triangle in the northwest of your frame. The night its drift measured 0.7 inches per minute, and the tail angle, if any, aligned with the anti-solar vector you annotated as a small arrow. The night-thin cirrus made every star a halo, and you learned to throw away most of what you shot. The night you tried comet rate guiding for the first time and the stars became short dashes like rain, and the target grew quiet and round in the centre. The night a breeze lined the grass and you could hear the field as a texture more than a sound. And the timestamp in your Fitz header was the only proof that time was still passing. None of these nights is famous, all of them are yours. You start to see connections to the first people who kept calendars by the rise of a bright wanderer, to the survey teams who built machines that look without tiring, to the patient amateurs who will observe a faint smear for weeks and never post a photo because the photo is not the point. You see how a shared sky makes collaborators of strangers. Someone at a different latitude confirms your rate. Someone with a bigger mirror sets a limit on gas lines. Someone with a heliophysics camera catches the moment when dust shifts direction. Someone in the infrared turns reflected light into size and albedo instead of guess and metaphor. You realise that the word we can be as small as you and your mount or as large as a planet's worth of eyes. On some nights it will be hard to stay with it. Clouds will lurk, batteries will sulk, a cable will snag, a clock will be wrong by just enough to make the first hour useless. Those nights are part of the practice. You learn to treat trouble like weather. Note it, correct it if you can, and keep the thing you came for in view. If the object is absent to your gear, it isn't absent to the sky. You can still step back, look up, and remember that your inability to record a photon is not the measure of whether the universe is generous. And then you will have a different kind of success. You will go home with nothing on your card and still feel that the night gave you something you did not have before. A deeper patience, a clearer respect, a steadier hand when the focus is almost but not quite there. In the days between sessions, you might find yourself checking ephemerides as often as other people check messages, watching the numbers drift. RA ticking eastward, December sliding towards some quiet limit, elongation widening and then narrowing. The phase angle telling you whether a tail would shine if there were grain on small and many. It's a log of a conversation in numbers, and it works on you the way a tide works on a beach, slowly changing what you notice, making you fluent in small differences. You catch yourself aligning errands with moonset, adjusting dinner to step into astronomical twilight, choosing a road that avoids the bright billboard that wrecked last week's frames. Your life bends gently to meet the sky, and the sky, as always, does not bend back. It doesn't need to. The bending is the belonging. Nothing about this visitor depends on you, and yet your experience depends on it in a way that feels personal. Its refusal to return makes each clear night feel unrepeatable. Its faintness makes each success a joint effort between the cosmos and your attention. Somewhere inside the routines, cool the sensor, due on, focus, confirm, plate solve, guide, another routine is forming. Line up your sense of scale with a larger one, line up your pace with a slower one, line up your wants with what the sky actually offers. That alignment is why you keep going outside when sleep would be easier. It's why a graph that slopes upward by 1/10 of a magnitude can feel like a cathedral window. It's why you can stand in a field and be both very small and very certain that being small is not a problem you have to fix. Morning will come, the files will transfer, you will open them, and they will look at first like last night's. A smudge, a drift, a familiar field. And then you'll lay tonight over last night, blink them, measure the shift, check the annotation, and the difference will step forward like a whispered truth. You finally heard, it moved, you moved, the world turned, and through all of it, something from far away crossed your patch of sky without hurry or apology. You'll write a line in your notes that would bore anyone else. Delta equals 0.78 AU, rate 0.6 inches per minute, PA motion 102 degrees, no gas lines, coma 0.9. Arc minutes. And you will close the notebook like a door that leads to a room you can re-enter later. The room will still be there, the visitor will not. But the skill of finding it, the habit of listening long enough for faint things to speak, the way your breath slowed in the dark and matched the quiet pace of a universe not designed around you, those will remain, and they will be what you keep returning to night after night, like coordinates that are not on any chart except the one you draw by going outside and looking up. If you've made it here, thank you for staying with me in the quiet, through coordinates and clocks, through star fields that look the same until you learn how to see them differently, through a one-time visitor that reminded us how much patience can reveal. If tonight's journey helped you unwind, breathe a little deeper, or simply feel more at home under the sky, consider tapping subscribe and turning on the bell so this little corner of calm finds you again when you need it. It's a small gesture that keeps this channel alive and lets me keep making gentle, curiosity-filled films you can drift off to. And if you think someone you love would rest better listening to distant light and slow ideas, feel free to share this with them, softly, like passing along a warm blanket. I'd love to hear from you too. Tell me in the comments, what moments stayed with you tonight? Was it the sidereal clock ticking 4 silent minutes faster than our days? The way a faint coma can hide in a bright sky, or the comfort of knowing that not every traveller is a threat, some are simply guests who pass without knocking. Maybe you've had your own backyard rituals. A thermos, a chair that wobbles a little on uneven ground, a stubborn cable that somehow always loops the wrong way. Those small details are part of this practice, and your notes might be exactly what a first-time stargazer needs to feel brave enough to look up. If you'd like more slow astronomy while you rest, videos about why twilight has colours that don't have names, about how dust becomes planets and sometimes just stays dust, about the way comets sketch their own calendars across the ecliptic, you'll find them on this channel. I make each one with the same intention, clear, unhurried, precise where it matters and soft where it helps. You can queue one up for later, or let autoplay choose something gentle for you. If sleep arrives before the credits do, that's a victory, not a problem. Your body figured out what to keep and what to let go. For the insomniacs and the overthinkers, you're welcome here. You don't have to remember the formulas to receive the feeling. You don't have to finish the thought to feel it settle. Let the numbers be like rain on a roof. Real, rhythmic, nothing to fix. If you're listening with your eyes closed, imagine the sky you would draw if you could. Maybe fewer streetlights, maybe a horizon without any buildings, maybe just enough chill in the air to make the stars sound a little crisper. Hold that for a breath or two, then let it go. Thank you to everyone who supports this work, by watching, by commenting, by quietly letting a playlist run in the background while you drift. You're the reason I can keep turning long, careful research into something friendly and easy to rest to. If you'd like to help more directly, there are links in the description. Ways to vote on future topics, join a sleepy little community of curious night owls, or simply tip a cup of coffee towards the next script. None of that is required. Your time is already a gift. Before we dim the lights completely, a simple reminder you can take with you: the sky repeats, but it's never the same. Our clocks and coordinates make patterns, and patterns can feel like loops, but what moves through those patterns, our questions, our attention, and sometimes a traveller from another sun, is always new. If you need calm tomorrow, it will be here. If you need wonder, it will be here. And if you only need a voice to keep you company while the world gets quiet, that will be here too. So loosen your jaw, drop your shoulders, and unclench the hands you forgot you were clenching. Let the last of the day slide away like a shadow leaving the frame. The sky can take it. That's what it's for. Wherever you are, whatever time it is, I'm grateful we met here, in this little interval between questions and sleep. Until next time, be gentle with your hours, keep a small place for wonder, and when you're ready, close your eyes and let the universe keep watch for you. Good night and clear skies.